The next topic is electric circuits. In this topic we will first learn about electrical quantities, and this is what we will be learning. Units of measurement. The unit of charge is coulombs. Calculating areas of circles. By the way, this is the math you need to know before we actually start the lesson. This is not what we will be learning, but we will start with electrical quantities. So you have already learned this math previously. Now use of standard form. Standard form is also called scientific notation. Then ordinary form, that is the decimal form, the normal way we write the number. And representing the charge on an electron, you would have learned that the elementary charge in the previous lessons. You would have learned that elementary charge is the charge on a magnitude of charge on a proton or an electron, which is 1.6 into 10 to the power of minus 19 coulombs. You don't need to memorize it, it will be given to you, but when you do a number of questions you will automatically memorize it. Then changing the subject of an equation. This is O-level mathematics, and this is where we will apply this for this lesson. Finding the resistivity of a material from an object's resistance. That is where you will be using this. You will have the equation R equals rho L over A, and you may need to make rho, which is the resistivity, the subject of the equation. We will see all that. Substituting numerical values into algebraic equations. Example using the transport equation. So there is one equation which is called the transport equation, and that is I equals NAVQ. I is the current, N is the number density, which is the number of charge carriers per cubic meter. We will see this in detail. I equals NAVQ. A is the area of cross section of the conductor, V is the drift speed, Q is the charge on a charge carrier in that material. If it's a wire, then the charge carriers are electrons, so Q will be the charge of an electron. We change the equation then to I equals NAVE. Substituting numerical values into algebraic equation. So that is where we will be using this transport equation. I equals NAVQ. Determine the slope of a linear graph. So very simple. You know how to find the gradient or slope of a line. That is change in y divided by the change in the corresponding x coordinates. Finding the resistivity from experimental results. So if you review the lesson on resistivity, you can see the graph and the gradient of the graph as well, and how to determine the resistivity from the gradient of the graph. Okay, so this is what you would have learned before, and this you can see what will I study in this chapter. So atomic structure and the structure of solid material. So we will see this in detail. Now when we start with the first subchapter, that is part 1 of chapter 3.1, we start with electric current. So by the end of this section you should be able to describe electric current as the rate of flow of charged particles. Make calculations of electric current. You have to know the definition of electric current. So it is the rate of flow of charged particles. The charged particles, actually when they move you get a current. So the rate of flow of charged particles is the current. Then we have learned this, the elementary charge, which is 1.6 into 10 to the power of minus 19 coulombs. That is the charge on a proton, and if you take the magnitude of the charge, it will be the same as that on an electron. Magnitude means the size without considering the sign. The unit of charge is coulombs. Then so if you have n number of, let's say, protons, and that number of protons is let's say this much, then the total charge will be the number of protons times the charge on a single proton, which is this much. So you get then 1 coulomb. So in 1 coulomb of charge, it can be either 1 coulomb of negative charge or 1 coulomb of positive charge. If it's 1 coulomb of positive charge, then you have this number of protons in it. If it's 1 coulomb of negative charge, then you have this number of electrons in it. And the charge on a proton or an electron is fixed. So if it's a proton, it will have plus 1.6 into 10 to the power of minus 19 coulombs. If it's an electron, it will have minus 1.6 into 10 to the power of minus 19 coulombs. This amount, it will not change for one electron. this is the amount of charge. For one proton, this is the amount of charge. So if it's an electron, obviously it's this with a negative sign in front, because electrons are negatively charged. If it's proton, then it's this number with a positive sign in front of it. If it's positive, sometimes we don't even write the positive sign, but if it's negative, we will have to write the negative sign. Electric current is a measure of the rate of movement of electric charge. Lightning strikes can have currents of 10,000 amperes. Now we will see the equation for current. That is this. Current is charge passing a point divided by the time for that charge to pass. You have learned that the unit of charge is capital C, that is Coulomb, and the unit of time is second. So coulombs per second is ampere. By the way, ampere is a SI base unit. You have learned that in the AS class. I think it was the very first chapter in the AS lessons. You learned the 7 SI base units: meter, second, ampere, mole, candela, so there was a list of about 7 base units, and ampere is a base unit. So this unit Coulomb is actually derived from the unit ampere second. Ampere second is Coulomb. So if you rearrange this equation to this, make Q the subject of the equation, then you get Q equals IT, and if you look at the corresponding units, then Coulomb is equal to ampere second. So Coulomb is the derived unit, ampere is a SI base unit, second is also an SI base unit. I mentioned this because some students look at this equation and think that ampere is the derived unit, because ampere equals coulombs per second. Some students think that ampere is the derived unit, coulomb and seconds are the base units. That's what some students think. But remember, coulomb is the base unit, ampere and second are the SI base units. Now, if charge moves, this is referred to as an electric current. I mentioned this earlier. And the strict definition of current is the rate of movement of charge. You can figure out the definition from this equation. Now, in a wire, the charge carriers are electrons, and here is a simple circuit. You have a battery, a number of cells form a battery. This dashed line is used to indicate that there are a number of cells in between this cell and this cell. So a collection of cells or a number of cells form a battery. This is a battery here. This is the symbol for a battery. Then here you have a wire. Then this is the symbol for ammeter. This is the symbol for lamp or bulb. And here is another wire. Now these arrows indicate the direction of flow of current. Current flows from the positive terminal to the negative terminal outside the battery. Inside the battery, the current flows from the negative terminal to the positive terminal. But actually what is flowing here is the electrons. So the electrons move from the negative terminal to the positive terminal outside the battery. So that's why we say that direction of conventional current is opposite to the direction of movement of negative charges. Always the direction of current is opposite to the direction of movement of negative charges. Now if you have positive charges, let's say for example protons or alpha particles moving in a certain direction, that is the direction of flow of current. Then the current is the direction of movement of positive charges or a charge, and it is opposite to the direction of movement of negative charges. Now previously, even for chemistry, you would have learned about the metallic bond. Now in the metallic bond you have conduction electrons. So wires are made up of metals, and these metals have metallic bonds, and in the metallic bond you have the sea of electrons, which are the conduction electrons. So these conduction electrons conduct the current. That's why, because there are free electrons in metals, that's the reason metals are good conductors of electricity. So let's go through this now very quickly. I think you will understand it much better now because I already explained. So here we learn this. Now we later afterwards in the next page we will see the calculation of electric current. Some particles have an electric charge. For example, the electron has a negative charge. In SI units, electric charge is measured in coulombs, and the amount of charge on a single electron in these units is 1.6 into 10 to the power minus 19 coulombs, because this is an electron. Electron has a negative charge, and on one electron, this is the amount of charge. This means that you would have 1 coulomb of negative charge if you collected together this number of electrons. So to get 1 coulomb, now this is the amount of charge in 1 electron. So what you can do is 1 electron, maybe I can even write it here. So if you want to find the number of electrons that you need to form 1 coulomb of charge, you can do this calculation. I don't think the textbook has really shown it, but I will show you how to figure it out now. It's very simple mathematics. Now you know the charge on 1 electron is 1.6. It's already given. It's also given in your data sheet. In the exam paper also you will see it in the data sheet. So I will use the symbol E for electron. So 1 electron has a charge of 1.6 into 10 to the power of minus 19 coulombs. Okay, so if you want to find for 1 coulomb, so simple ratio and proportion, then what is the number of electrons? So we will write this as a fraction. Now you know this is the conversion factor. 1 electron has this much, so we can write it like this: 1 electron has a charge of 1.6 into 10 to the power of minus 19 coulombs. Therefore, so times 1 coulomb has how many electrons? Now you can see the way I wrote this. Now you can use this method for any unit conversion. Almost any unit conversion you can use this method. Okay, if it's in proportion to the other, one quantity is in proportion to the other quantity. So what we do is we write the quantity that we need finally in the numerator, the quantity that we want to get rid of, the unit that we want to get rid of, we write in the denominator so that it cancels out like this. Now what you can do is you can divide, you can perform this calculation even, you can use your calculator right now and then enter 1 divided by, make sure you write the fraction like this, 1 over, this whole thing should be in the denominator, so 1.6 into 10 to the power of minus 19 coulombs. So what we get is 6.25. You can try it with your calculator now. 6.25 into 10 to the power of 18. Now see, we are left with this unit or symbol, so electrons. Remember I told you I am using the letter E for electron. So we can see that 1 coulomb of electrons, sorry, 1 coulomb of charge, if it is to do with the 1 number of electrons that is forming 1 coulomb of charge, then you will need 6.25 into 10 to the power of 18 electrons. So you can see that here also. And I think my explanation is much clearer than what is here. The charges on fundamental particles such as electrons are fixed properties of these particles. So I mentioned that several times earlier. It is impossible to create or destroy charge. The total charge must always be conserved. Then electric current, if an electric current moves, sorry, if an electric charge moves, this is referred to as an electric current, and the strict definition of current is the rate of movement of charge. As it is usually a physical movement of billions of tiny charged particles, such charge movement are often said to flow. Such charge movements are often said to flow. Okay, so that's why we say rate of flow of charge is a current, because there is a physical movement of billions of tiny charged particles. Thinking of the flow of charge like the current in a river can be useful, and we will see later how current splits and recombines at circuit junctions in a manner that is analogous to water flow. So in the O-level class also you would have learned this: the sum of currents entering a junction is equal to the sum of currents leaving that junction, because charge has to be conserved. Moreover, as the total amount of charge in a river at a given time does not change even if the river splits, this again illustrates the conservation of charge. So you can think of the charge like water. So let's say you have a certain amount of water flowing in a river, and then the river branches. So at that branch the total amount of water flowing to the branch should be equal to the total amount of water leaving the point where the branches form. Entering the total amount of water entering the branch should be equal to the total amount of water leaving that point where that branch is. We can measure the electric current through a component using an ammeter connected in series. So you have learned about the ammeter. The ammeter, so here we have the symbol for ammeter. This is an actual ammeter. We can even use a multimeter as an ammeter. By the way, I have uploaded some videos explaining how to use the multimeter as an ammeter, voltmeter, and also an ohm meter. You can watch that video for more details. So here this is just an ammeter, but in our physics labs we have multimeters which can be used for several purposes, like for checking conductance, for using it as an ammeter, multimeter, then ohm meter is used to measure resistance. Electric current occurs when a charged particle which is free to move experiences an electric force. So when there is an electric force on a charge, that attracts or repels the charge, so which causes the charge to move. So when the charge is moving, you get a current. Remember, like charges repel, unlike charges attract. So what causes this attraction or repulsion is the like or opposite charges. For example, if you look at the terminal of a battery, now this is the positive terminal and this is the negative terminal. So electrons flow this way because the negative terminal repels and the positive terminal attracts the electrons. If it can move, it will be accelerated by the force. This movement of charge forms the electric current. Most electric circuits are made from metal wiring in which there are electrons that are free to move. These conduction electrons then form the current. Any source of electrical energy can create an electric force in order to produce a current. In figure C, you can see here, the cell causes the electric force experienced by the negative conduction electrons. So they move through the metal. They are attracted to the positive anode of the cell. So this is the positive terminal. We all can also call it the anode. This is the cathode. The negative terminal is the cathode. Cathode is negatively charged. Anode is positively charged. So remember, when you learned chemistry, you would have learned chemistry and you would have learned about electrolysis. So cathode attracts cations. So the cathode is negatively charged. Anode attracts anions. Therefore, anode is positively charged. You would have learned that for chemistry. Conventional current flows from positive to negative. Negative electrons would move in the opposite direction. So I already explained all this. Now this entire page should be extremely clear to you. Now we will see the equation for current, and this also can be used for the definition of current. Anyway, at the end of each subchapter you have the definitions given, so make sure you study this, because in the exam paper they can ask you to write down these definitions. And study means you memorize these definitions with understanding, because if you try to write it in your own words, you may miss certain keywords that are required in the definition. So this happens to some students. They try to write the definition in their own words and they miss the certain keywords that are required according to the mark scheme, and if those keywords are not there, they can't score, the student can't score the full marks. That's why I tell the students, when it comes to definitions, memorize them with understanding so that you will not miss the relevant keywords when you write the definition. Okay, so now let's go to the next page. The SI unit of current is the ampere. A current can be calculated from the equation. So here we have a very important equation. You will use this equation again and again. I think even in the Edexcel 921 or Cambridge O-Level or IGCSE AQA OCR classes also you would have learned this equation. Thus, now according to this equation, you can see 1 ampere. Here, to get 1 ampere, it should be a 1 coulomb divided by 1 second. So we can write try to explain what is 1 ampere that way. Thus 1 ampere is the movement of 1 coulomb of charge per second. For example, if the lightning strike in figure A, so over here, for example, you can actually do this with a Van der Graaf generator also. Okay, so I have uploaded a video showing that this can be done with a Van der Graaf generator. You can watch the video. There's a video on my channel under physics experiments, I think. You can see Van der Graaf generator, or just search on my channel Van der Graaf generator and the name of the channel. You should be able to see that video, and there you can see the lightning there, the spark there. Okay, so for example, if the lightning strike in figure A takes 0.1 seconds to transfer 1150 coulombs of charge, we could calculate the current in the lightning. So again, very simple, use the equation. So the current is charge over time. The amount of charge flowing is 1150 coulombs in a time of 0.1 seconds. So you get this, and remember, all are in SI units, so you will get your answer also in SI units. The equation defining electric charge is often used in a rearranged form to find delta Q, that is the amount of charge. The amount of charge, yeah, they are mentioning that has moved through a component in a given time. So amount of charge that has moved or flown in the delta t period of time. So that's why when you rearrange this, you get this. You could remember this as quilt equation, Q equals IT. Whatever way you find easier, you can remember it. Okay, so here you can see the Van der Graaf generator, and so in unit 3, unit 6 papers, you have these kinds of experiments. So we will go through that. Let's see. Alright, so observing charge flow, we can monitor small movements of charge to see how they form a current using a hanging ball that will conduct electricity. So here you can see this is the hanging ball. Then we have this Van der Graaf generator. So what we do is we turn this. Now when we turn this, this gets more and more charged. As a result, this will also get more and more charged. Let's say if this gets more and more positively charged. Now since you can see the charge can go like this, so this would become more and more negatively charged. So we will see what happens. A suspended ball can carry small number of electrons across a high voltage gap. So when this is highly positive and then this is highly negative, that will create a high voltage gap here. There will be a big potential difference between this and this. So as a result, there will be charge induced on this insulated ball, and it will be attracted. Now what will happen is, if this side is highly positively charged and this side is highly negatively charged, what will happen is this side positive. Now you can imagine you would have learned about induced charge or induction in the O-level classes when you learned about static electricity. So there will be the electrons will be attracted to this side of the ball, and the electrons on this side will be repelled, because this is negative, this is positive. So the electrons will be attracted to this side and the electrons will be repelled from this side. So this side will gain a slight positive charge, this side will gain a slight negative charge. Now when more and more charge on either side of this plate and this plate builds up, then more and more electrons will accumulate on this side, and this side will be more and more negative, this side of the ball will be more and more positive. So eventually when the charge build is large enough, what will happen? This ball will be attracted to this and it will touch this. Now what will happen is, when it touch, it gets discharged. Okay, some negative charges jump to this to try to neutralize this. Then what will happen? When it loses its charge, it will go back. The reason it was attracted to this was because of the build-up of charge. So once it builds up a lot, it will jump to this and eventually it will get discharged when it touches this. So it will go back, and then again the same thing happens. This process continues. Okay, so we will see what the details now. A suspended ball can carry small numbers of electrons across a high voltage gap, and this current is measured using a spot galvanometer. You can see the high voltage setup across the air gap between the metal plates encourages negative electrons to want to move towards the positive side. So this is what I explained. The hanging ball is painted with conducting paint. So outside you can imagine it's painted in conducting paint, and swings backwards and forwards across the gap. So once it gets discharged, it comes back this way. Now when it comes back this way, it can hit this, and then again we can see that process. So when it hits this, now it can gain some negative charges, and then again it will hit this. So then those negative charges are transferred to this, you see. So it will go back, hit this, some electrons jump to this, and as a result of the negative charge, it's attracted to this, hits this, gets neutralized, and due to the momentum it comes back and hits this, and this way it can conduct charge across the gap. The hanging ball is painted with conducting paint and swings backwards and forwards across the gap, ferrying a small quantity of electrons from one metal plate to the other each time. We can measure this small movement of charge on a very sensitive ammeter. This is ammeter, very sensitive ammeter. We can use a galvanometer. So which very sensitive ammeter, we can also call it a galvanometer. So we use a galvanometer for this purpose. If we use the period of oscillation of the shuttling ball, which is this here, this moves back and forth like the shuttlecock when you play badminton. It's going back and forth, back and forth. So shuttling ball, and the tiny current. So this, you know, when it moves from here to here, it transfers charge. So when there is movement of charge, we say there is a current. We can calculate how many electrons would pass across one each journey of the ball. So using this, we can see the amount of current using this galvanometer. If the ball is shuttling too fast to be timed by eye, then we can use a stroboscope to measure the frequency of oscillations. Now if you don't know what a stroboscope is, there are some videos online. If you type stroboscope, how it works, you can have a good understanding, but briefly I will tell you there are different types of stroboscope. One is a stroboscope that flashes light. Now for example, let's say your ceiling fan is turned on, and you want to see how many turns it is making, let's say in 1 second, or how many rotations, or how much time it takes to complete one rotation, which is the period. So if you want to find the frequency or the period, you can use the stroboscope for that purpose. So let's say you have a fan that is turned on, and then you have a stroboscope. The stroboscope makes flashes of light, and you can adjust the frequency at which it makes flashes of light. So what you can do is you can reduce the amount of light intensity in your room, turn on the fan, and be careful when you flash the stroboscope, it will, and if you get the right frequency that the light is flashing from your stroboscope onto the fan will appear stationary. It will appear stationary, but it is turning. So what is basically happening is that when the fan completes, let's say, one turn, one rotation, if you adjust the frequency of the stroboscope, you can adjust it manually, you can see, and you can adjust it. So what you do is, now let's say the fan turns one rotation, so, and exactly at one rotation light flashes from the stroboscope. You can imagine that the stroboscope is like a gun which is flashing light. So it flashes a light. Then as soon as the fan completes the second turn, it flashes light. Third turn, it flashes light. So you can see the frequency at which light flashes onto the fan is equal to the frequency of rotation of the fan. So this way you can find the frequency of the fan, because that is matching the frequency on the stroboscope, and you can see the frequency that the light is flashing on the stroboscope. Okay, now when that happens, because after every rotation the light flashes on the fan may appear stationary. That's why you have to be careful. You might think the fan is stationary, and if you try to touch it, it's still turning, so it can injure you. So you have to be careful when you do this kind of experiment. Like I said, there are a lot of videos even showing you that it is done. So if you go just online and type stroboscope experiment or something like that, you will be able to see a very nice video on how it is done. Okay, stroboscope to measure the frequency of oscillation. So example calculation: if the spot galvanometer registers 6.5 microamperes, so you know galvanometer is like ammeter, it can measure the current, and the ball takes 2.0 milliseconds for one swing. So going like this and back, that is one swing takes 2.0 milliseconds. This is the period of oscillation. How many electrons does it carry on each pass from the negative plate to the positive one? So we have Q equals IT, and the current is given, the period is given, and then this is the amount of charge. Now how many electrons? So we know that one electron has a charge of this much. So if you want to find the number of electrons, so this is the amount of charge, 13 nanocoulombs. Nano is 10 to the power of minus 9. So this 13 nanocoulombs divided by, now one electron has this much charge, so then you can find the number of electrons. This is similar to what we did earlier, like this. So one electron has this much charge, then for the amount of charge that is given in this, you can see that the charge is this much, 13 nanocoulombs. So instead of 1 here, now you can write 13 nanocoulombs, and that you will get the number of electrons, and that will be this many. So in one swing it transfers this many electrons from one plate to the other, Note that on the ball's return journey it will be positively charged. Yeah, so it loses its negative charge when it touches this, and let's say all the electrons are all the electrons are transferred, then it can gain a positive charge when it touches this. So then it will be repelled by this, it will be attracted to this, having lost an excess of electrons when contacting the positively charged plate. However, the positive charge moving in the opposite direction still constitutes a current, and it will be at the same rate, the same current, because the ball speed is constant. Okay, then ionic charge carriers. Now so far we saw that electrons are carrying charge, but if you have movement of ions, any movement of charged particles is a flow of current. Now I told you previously, even if you have an alpha particle, that is a helium nucleus moving, then also you get a current, because you have a charged particle moving, that is a current. If the circuit is more unusual, there may be other charged particles, charge carriers, which can move to form the electric current. And in electrolysis you had ions. In the electrolysis, the electrolyte can be a molten substance, or it can also be a solution. So if it's a solution, you have the different ions. Now it's a molten solution, you have the ions. So these ions are what is moving in the electrolyte. So the ions carry charge because they carry a current when they move. When they move, the charge particle moving means a current. So charge carriers can move to form the electric current. For example, in the electrolytic, so here you can see, now it's explained, electrolytic processing of bauxite ore to produce aluminium metal. The bauxite is dissolved in cryolite, another aluminium compound, and this solution then has free aluminium ions, which are charge carriers. So if it has a charge, if it's a charged particle, it's a charge carrier that can move through the liquid as an electric current. These ions are positively charged and move because of the electric force towards the negative cathode. This is an electric circuit. This is still an electric circuit that must obey the rule of conservation of charge, and in which we can measure the current as the rate of flow of charge. So for chemistry, you would have done this electrolysis calculations, and you would have seen the conservation of charge, but we will see a simple example after this. As the charge on an electron is a fixed negative amount, we can easily calculate the charge on any ion. So you know the charge on an electron is magnitude of charge is this much. It's actually, if it's an electron, it's minus, so this much. So if we know that the charge on an ion is a certain amount, you know it's n number of or n number of electrons which form that negative charge, because it is the electron which is a fundamental particle. So you can have a charge that is less than this, that is split from the number here. So if you have an iron, then it will have maybe 3, minus 3, minus 5, plus 7, something like that. So you can see then for each plus or each minus, you multiply by the charge on a proton or an electron to get the total amount of charge, or you can find the number of electrons it is lacking or it has in excess to form that amount of charge. As the charge on an electron is a fixed amount, we can easily calculate the charge on any ion. This would be important in a situation where ions were moving as the charge carriers in an electric current. For example, in electrolysis, the charge on a proton is the same magnitude as that on an electron but is positive. So plus 1.6 into 10 to the power of minus 19 coulombs. Remember that number, but you will automatically remember it once you do a number of questions. So again, very simple. Here you can see what would be the charge on an ion 3. Ion. So ion 3 ion, ION ion here. IRON is the element Fe. So this is a ion 3 ion. So it is Fe 3 plus. Those students who have done or is doing chemistry will find this very simple. So this means the ion is having a charge of plus 3. That means it has, we can say, lost 3 electrons. So now it has a net charge of plus 3, which is 3 times the elementary charge. 3 electrons have been lost, so the net charge is that of the ion's 3 excess protons. So if you consider an atom, the number of protons is equal to the number of electrons. That's why the atom is electrically neutral. So if it loses 3 electrons, then it will have plus 3 charge. So this will be 3 times the elementary charge, which is this, and so it will be plus this. Now remember, it has to be positive because it has lost 3 electrons. According to this, you can see that, and this plus 3 means 3 times the elementary charge, which is the charge on a proton. And so the charge on this ion is actually this many coulombs. So we have come to the end of the lesson. Now make sure you answer all these questions and check the answers in the answer script. Okay, now we have come to the end of the lesson. Now I mentioned earlier that these definitions are very important. Make sure you memorize them with understanding. Also again, do these questions. This will test whether you understood the theory well. And by the way, for chemistry you would have learned this Avogadro's number. That is 1 mole of any particles has this number of particles in it. So for example, 1 mole of copper atoms, in 1 mole of copper atoms you get this many number of copper atoms. So if it's 1 mole, remember it's always this number. If you say 1 mole of water molecules, then you have 6.02 into 10 to the power of 23 water molecules. If you say 1 mole of let's say ions, then you have this number of ions. Now if you take 1 mole of water molecules, that you know is this number of water molecules. Now each water molecule has 2 hydrogen atoms and 1 oxygen atom. Each water molecule, H2O, 2 hydrogen atoms and 1 oxygen atom. So if you take if you say 1 mole of in 1 mole of water molecules, how many oxygen atoms are there? It is the same number. But how many hydrogen atoms are there? 2 times this number. Because 1 mole of water molecules has this number of water molecules, and each water molecule has 1 atom, which is equal to the, for 1 water molecule you have 1 oxygen atom. So that means you have this number of oxygen atoms in 1 mole of water. But each water molecule has 2 atoms of hydrogen. So 2 times this number of hydrogen atoms are there in 1 mole of water. Charge is a fundamental property of some particles. It is the cause of electromagnetic force and is a basic aspect of describing electrical effects. Charge is measured in coulombs. 1 coulomb of this is the symbol of coulomb, capital C. 1 coulomb is the quantity of charge that passes a point in a conductor per second when 1 ampere of current is flowing in the conductor. So you can figure that out from the equation. So if it's 1 ampere, you get see, it's given here 1 ampere is the movement of 1 coulomb of charge per second. So to get 1 ampere, you should have 1 coulomb of charge passing per second. That is what is explained here. 1 coulomb is the quantity of charge that passes a point in a conductor per second when 1 ampere of current is flowing in the conductor. The amount of charge on a single electron in these units is 1 minus 1.6 into 10 to the power of minus 19 coulombs. Now why the minus sign? Because electron is negatively charged. If it's the charge on a proton, it will be plus this number. You'll have plus sign and the same number. Electric current is the rate of flow of charge. Current can be calculated from the equation. So current is charge passing a point divided in coulombs. Current in amperes is equal to charge passing a point in coulombs divided by time for the charge to pass. So this is the equation in symbols, and I explained this. So you can figure this out also from the equation. 1 ampere, if you substitute, is 1 coulomb per second. Alright, so we have come to that end of that lesson 3.1, chapter 3, part 1 was complete. 3.1 part 1 was complete. And now if you go back to the objectives, you can see here, describe the electric current as the rate of flow of charged particles. We learned that. Make calculations of electric current. So we did both of that. Very simple. You have to simply use this equation, and remember, one electron or one proton has this magnitude of charge. Only difference is the sign. And let's say some ion has ion, okay, ion has let's say if it's copper 2 plus, then the charge in coulombs on that copper 2 plus ion is 2 times this number. Okay, so yeah, so we have come to the end of this lesson now. Yeah, so if you have any questions, you can let me know now. And also just for the audience that is watching this online, students who are watching this online, just type whatever you found most appealing or something that is important here. Just type that in the comments below, so that you can benefit from it, because when you type, it will help you to review what you learned, and also the other students can also benefit from it. So make sure you type a comment, and if you enjoyed the video, share it with someone who wants it. Also see the video description for more information about the courses, the content, about our online classes. There will be a link to some important important information in the video description. So check that out, leave a comment and like the video. Yeah, so I will see you all in the next video.